We're going to use Kirchoffs rules to solve circuits, and these are circuits that are slightly more complex than just a simple series parallel or combined series and parallel. Some of the same rules still apply, right? We still know that current is the same everywhere in a series circuit, and we're going to need to know that. We're going to take advantage of that rule. We also know that the power that's produced by the batteries and consumed by the other components has to add up to zero. We're going to take advantage of that. So Kirchoff's two rules tell us that the potential difference for all components around any closed path in an electrical circuit is zero. What we mean by that is if we have a battery and then we put something in it, right, there's a voltage drop across this resistor and it has to equal the voltage increase of this battery. So however much voltage or potential difference the battery supplies, the resistor has to consume, I suppose. And also the amount of current that flows into a junction has to flow out of the junction. So the amount of current in has to equal the amount of current out. Now, that's a little bit weird. Let's take a look at this circuit. It's slightly complex in that we have 4 power supplies in it, and then there's also 3 branches. Here's a branch between junction 1 and junction 2, here's a branch between junction 1 and junction 2, and here's a branch between junction 1 and junction 2. Not only are there 3 branches, there's 3 loops. We can go through the left loop, we can have current flowing through the right loop, and we can have current that flows all the way around the loop. So this is a fairly complex thing with lots of power supplies, lots of resistors. So we're going to analyze this by first assigning a direction that the current flows in each loop. And this is arbitrary. You can pick whatever you want, doesn't matter. Okay, so here this arrow points in this direction, so this is the current through our left loop or our left branch. This is the current for our middle branch and the current for our right branch. And we do that so we can assign pluses and minuses on our resistors. We assume that current comes into the positive side of a resistor and leaves the negative side of a resistor. So we're going to label each resistor with a plus minus, plus minus, plus minus, depending on which way current flows. Okay, so we've done that. Now the next thing we need to do is we need to apply the 2 rules. And the two rules says that the sum of the voltage is 0 and the sum of the current in equals the sum of the current out. Okay. Now how do we know how to do that? Well, the reason we know is we've put these signs on different things. Also, we know the signs on batteries. A battery is positive on the long side and negative on the short side. Positive, negative, positive, negative. So we don't need to label those because we already know them. But remember, the long side of the battery is positive. So let's take a look at what this says to do. Okay, we're going to write an equation for each loop. To do this, we add the potential differences going around the loop in any direction. We don't have to go in the direction of our assumed current. For the potential differences across each, we use these 2 rules. The potential differences for an ideal battery and a power supply is positive when we go from negative to positive, and it's negative when going from positive to negative. The same is true for resistors. The potential difference for a resistor, remember voltage according to Ohm's law is current times resistance, we assign it as positive when we go from negative to positive and negative when positive to negative. So we're going to write an equation for each one of these things. Okay, and then we write a junction equation for one of the junctions. So we're going to simplify and set up all this stuff, and then we are going to have to do some simultaneous equations to solve for this stuff. Okay, so let's take a look at what that looks like. Let me go back and look at this circuit. Okay, so let's use Kirchoff's rules to solve this circuit. Alright, so we've labeled our currents through the circuits. Over here on the left-hand loop I have I1, over here on the right-hand loop I have I3, and through this middle branch I have I2, and we're actually going to have to use all of those. So write a loop equation for the right-hand loop of the circuit for this sample. We can do that. It's a little bit complex, but not bad. So let's take a look. I'm going to do this in red. Alright, so we're going through the right-hand loop of the circuit, and I need a starting point. I'm going to start here at junction 1. Now, the first thing I see is I3 through this resistor, this 10 ohm resistor. It goes from positive to negative, which means that's a negative voltage. So remember, voltage equals current times resistance, and for a resistor, if it goes from positive to negative, we use negative. So I have negative 10 ohms times the current I3. So negative 10 I3. Then I go to my next element, and I have this 4-volt battery here, and it goes negative positive. Since it ends with positive, I know I just add on my 4. And then continuing around, positive to negative, this is 20 I3, but it ends negative, so plus a negative 20 times I3. And then if I continue around, positive to negative, so this is still I3 through this branch, and it's times a 2 ohm, so minus 2 times I3. And then I'm to my junction, and I'm going to go up through this junction here. This is also positive to negative, but this is I2 now, so this is minus 5 I2, and then positive to negative on this battery, that's a 6-volt battery, so minus 6 volts equals 0. So all of these things have to add up to 0 around that loop. Now we're going to do the exact same thing for the left-hand loop. So I'm going to start in the same spot, and I'm going to go this way around my loop. Doesn't matter, but that's just the way I picked. Okay. So again, let's get started. I have, and I'm going to do this one in blue. So make my marker the right size. I have through here, I'm going through here, so negative to positive, that's positive. So I have 6 volts. Okay, negative to positive, this is I2, so plus 5 I2. Then I'm to this junction, I'm going this way, positive to negative, so that's minus 2, and this is in this branch over here, I have I1. And then positive to negative, so minus 8 volts, positive to negative, minus 8 I1, and then negative to positive, so plus 12 volts, and I'm back to where I started, so this equals 0. Now write in the junction equation for junction 1. Here's junction 1, and into junction 1 I have I1, it's going in, plus I2, it's also going in, minus I3 equals 0 because it's coming out. The other way I could have written this was I1 plus I2 equals I3. Now basically the only unknowns we have here are currents, right? And I have I1, I2, I3, and since I have 3 equations and 3 unknowns, I should be able to solve this. So put the loop equations and junction equations into the standard form shown in part 2 step 6. So if we go back and we look at part 2 step 6, it says to write it like this. I1 plus I2 plus I3 equals B1, I1 plus I2 plus I3 equals B2, I1 plus I2 plus I3 equals B3. Okay, so we're going to set this up so we have all our, this is essentially X, Y, Z constant, right? We're just doing linear equations, 3 linear equations, we're going to simultaneously solve them. So not really that hard, okay, just long. Okay, so we put these into our standard form, which means let's simplify a little bit. I'm going to start up here with this one. I have 6 volts and 4 volts, so that's negative 2 volts, and I'm going to add that over, so I have 2 on the right. Now I'm going to go through and find all my I1s, no I1s, so 0 I1 plus, how many I2s do I have? There's an I3, there's an I3, there's an I2, so minus 5 I2, minus 5 I2 plus, and now I have my I3s, 2I3, 22I3, 32I3, and those are all negative. So plus negative 32I3 equals 2. And then I've got to do the same thing for this equation. I've got negative 18, right? Minus 12 volts, minus 6 volts, negative 2, negative 10. Oh, I forgot that 8 volts, so I'm going to have to fix that. So equals, okay, so I've got 6 minus 8 plus 12. So 6 minus 8 is negative 2 plus 12 is 10. So over here I actually have 10 volts, negative 10, right? 18, negative 18, yeah, negative 10. That would have been bad. Negative 8I1, negative 2I1, so that's negative 10I1 plus I2. I've got 5I2 minus nothing, so plus 5I2 plus, and I have 0I3 equals negative 10, and then I have my last equation where I have I1 plus I2 plus I3 equals 0. So I1 plus I2 plus I3 equals 0. Solve the system of equations. Be sure to include any negative signs. There's a tool for this. The tool for this is your TI calculator. Now what I'm going to do is I'm going to push second quit and then I'm going to clear this all out. So I start on a home screen and let's see. The tool I want is called Solver, and if I hit the Apps button, Simultaneous Equation Solver, QRS. So I'm going to push alpha S and maybe it's called poly-simultaneous. So I'm going to go with alpha P, and here we have poly-simultaneous. Okay? I'm going to choose enter, enter, and we're going to do a simultaneous equation solver on 2. And so the number of equations we have is 3. The number of unknowns we have is also 3. Okay, enter. And now it's going to say, okay, well, put this in the matrix for us to solve. And we're just putting in our coefficients into this matrix. Okay, and that's the reason we write this like this. So our first one is this coefficient, which is 0. Our next one is -5, so I put in my -5. Our next one is -32, and our last -5, not -5, and then -32, and then 2. And then our next equation we have -10, +5, 0, and -10. And our last equation, we have I1 plus I2, so I have 1, 1, -1, because this is actually negative I3, right? When I subtracted it over, should have written that. And then 0, enter. And now I can push solve, and it gives me my solutions. And what do these mean? Alright, well, it says be sure to include any negative signs. So here's what this says. That equation says x1 equals 0.68, x2 equals -0.64. So x1, whoa, that was crazy. x1 equals 0.68, x2 is -0.64, and x3 equals 0.037. Now all that means is that we chose our currents correctly for 2 out of the 3 of them. The fact that x2, or I2 in this case, is negative simply indicates that we chose the wrong direction. So I1, 0.68, -0.64, and 0.037. And so the way we deal with this is we can actually say this current that we chose here is actually running the other way. So we have current going this way around this loop, this way around this loop. Okay, and so we have just solved for the current through each one of those things.